All right, let's talk about something you're using this very second, but you've probably never actually thought about. It's this invisible pulse that literally powers our entire digital world. We're going to pull back the curtain on the clock signal, the unseen conductor of, well, everything. So, to wrap your head around this, let's start with a question. Picture a giant orchestra. But instead of 100 musicians, you've got billions of them. And every single one needs to play their part at the exact same perfect infinitesimal moment. How on earth do you coordinate that? Well, believe it or not, that's exactly the problem that gets solved inside every single computer chip every second of every day. You see, those tiny little transistors, there are musicians. Each one has a simple job. Maybe it adds a number or stores a single bit of data. But if they don't all act together, in perfect unison, you get what's called digital chaos. A 1 might get read as 0, or a calculation might finish before it even has the right numbers to work with. That's a race condition, and it's the fast track to a system crash. You know, that dreaded blue screen or the spinning wheel of death. So how do we stop that from happening? The solution, and this is the beautiful part, is incredibly simple in concept. It's the clock signal. Just think of it like a digital metronome for our transistor orchestra. It sends out this constant, ridiculously fast electronic pulse, and every single component on the chip listens to that one beat. It's the master rhythm that forces everyone to act at the exact right moment. And when I say simple, I mean really simple. This signal isn't carrying complex information. It's just a square wave, a basic binary rhythm. It's either a high voltage state, let's call that on, or a low voltage state, off. On, off, on, off, over and over, billions of times a second. This relentless, predictable beat is the fundamental heartbeat of pretty much every digital device you own. So here's how the circuit actually uses that beat. It's like a little two-step dance. On the rising edge of that wave, that's when the signal goes from off to on, all the circuits do their thing. They perform their action. Then on the falling edge, when the signal goes from on back to off, they all get ready for the next action. This makes sure that everything happens in a perfect orderly sequence. Action, prepare, action, prepare. But here's the thing, this super simple on-off beat, it wasn't always this streamlined. Like just about any piece of technology, the clock signal has gone through a pretty dramatic evolution, all in the name of making things more efficient. If you go back to the early days, some chips needed what was called a 4-phase clock. I mean, can you imagine? 4 separate, overlapping signals just to keep time. It was super complicated. Then, in the 70s, famous chips like the Intel 8080 managed to simplify that down to a 2-phase clock. But that constant push for simplicity and efficiency eventually led us to where we are now. For most circuits, it's a single-phase clock. Just one elegant signal doing the work that used to take 4. Okay, so we've got our simple, single-phase clock. Problem solved, right? Well, not quite. See, creating the beat is one thing, but making sure that beat gets to billions of transistors at the exact same instant, that is a monumental engineering challenge. And just to give you an idea of the scale of this problem, it is staggering. In a modern high-performance chip, just sending the clock signal around to where it needs to go can eat up over 30% of the chip's total power. Think about that. A third of the energy is just for keeping time. That is a huge reason why your phone gets warm in your pocket or your laptop fan spins up. So why is it so ridiculously hard? Well, first, there's something called clock skew. Go back to our orchestra. Imagine the conductor's beat reaches the violinists a split second before it reaches the drummers in the back. Total chaos, right? That's clock skew. The signal physically takes time to travel, and even a few picoseconds of difference can cause major errors. Then there's the raw power needed, and keeping that signal a perfect, crisp square wave as it travels through what adds up to kilometers of microscopic wiring inside one tiny chip. It's a beast of a problem. The way engineers tackle this is with something called a clock distribution network, or more commonly, a clock tree. And it really is what it sounds like, this incredibly complex, branching, tree-like structure of wires and special amplifiers, all designed to deliver that clock pulse to every last corner of the chip with as little delay and skew as possible. It's basically a hidden masterpiece of electrical engineering. Now, as our chips get more and more powerful, that 30% power problem gets even bigger. It becomes a major bottleneck for things like battery life and overall performance. So, as you can imagine, engineers are coming up with some seriously clever ways to create smarter, more efficient rhythms. Today, we already use techniques like clock gating. It's a great idea. If a part of the chip isn't doing anything, we just stop sending it the beat. It's like turning off the lights in an empty room. Simple, but super effective. But the future, that's where things get really wild. People are working on resonant clocking, which basically recycles the clock's energy instead of just burning it as heat. And the holy grail might be on-chip optics, using pulses of light instead of electricity. Since light travels at, well, the speed of light, you could basically eliminate clock skew entirely. And this quote really nails why all of this matters so much. At the end of the day, every leap forward in computing speed, every new performance record that gets broken is ultimately constrained by how perfectly we can control this one simple, invisible pulse. It is the fundamental speed limit of the whole system. So, the clock signal started out as just a simple metronome. Now it's one of the most complex and power-hungry challenges in all of modern electronics. And as we start building chips with not just billions, but maybe trillions of transistors, the central question is still the same. How do we keep this ever-expanding orchestra playing in perfect harmonious time? The answer to that is going to define what computing looks like for decades to come.